We are witnessing a remarkable agent evolution, moving far beyond simple chatbots that just answer questions to highly sophisticated AI agents capable of executing complex, multi-step tasks across different systems. This leap is fueled by advancements in large language models that can understand nuanced instructions and interact with external tools. The future of computing is shifting from passive information retrieval to proactive, goal-oriented agentic systems. At its heart, a modern GPT-based assistant is a fusion of a powerful large language model, a set of initial instructions defining its purpose, and a crucial connection to external capabilities or tools. The LLM provides the reasoning and language understanding, while the instructions give it a specific persona and operational boundaries. It's this combination that forms the core anatomy of any intelligent agent. Crafting the initial instructions is like writing the origin story for your agent, defining its unique persona and guiding its every interaction. You can specify its tone, its area of expertise, and even its communication style, such as being a witty scientist or a formal business analyst. This initial prompt engineering is the most critical step in creating an effective and memorable agent. Explicit rules are the essential guardrails that ensure an agent's behavior remains consistent, predictable, and aligned with its intended purpose. These predefined constraints act as a safety net, preventing the agent from going off topic or performing unintended actions. By establishing guardrails, you create a reliable and trustworthy assistant. The functional leap from a simple conversationalist to a powerful analyst occurs when an agent gains the ability to interact with external systems and data. This is achieved through two key capabilities: the ability to execute code and the ability to connect to external services via APIs. These transform the agent from a mere text generator into a true systems analyst. Enabling code interpretation gives an agent a sandboxed Python environment, allowing it to perform incredibly complex data science tasks on the fly. You can upload a CSV file and instruct the agent to clean the data, perform statistical analysis, and generate visualizations without writing a single line of code yourself. This capability turns any user into a powerful data analyst. The magic behind safe code interpretation is a sandboxed execution environment, which is an isolated space where the agent can write and run Python code without any risk to your local machine. This environment comes preloaded with popular data science libraries like Pandas and Matplotlib, providing a powerful yet secure analytical toolkit. This mechanism is what allows for safe, on-the-fly data analysis. A truly effective data science agent follows a structured analytical path, beginning with data cleaning to handle missing values and correct data types. It then moves to exploratory data analysis using visualizations, calculates descriptive statistics, and can even perform hypothesis testing and predictive modeling. This systematic approach ensures a comprehensive and reliable analysis of any dataset. Custom actions are the ultimate tool for extending an agent's capabilities, allowing it to connect to virtually any external API or service. By defining a custom action, you can empower an agent to fetch real-time stock prices, search a product database, or even interact with your own custom-built applications. This is how you give your agent real-world superpowers. The OpenAPI specification is the universal language for describing APIs, making it the de facto standard for defining how an agent interacts with external tools. By providing an agent with an OpenAPI document, you're giving it a detailed map of the API's endpoints, parameters, and responses. This allows the agent to intelligently and autonomously construct the correct API calls to fulfill a user's request. A tool like Grok creates a secure tunnel from the public internet to a service running on your local machine, effectively giving it a public URL. This is crucial for development, as it allows a cloud-based agent to securely interact with a local development service without you having to deploy it to a public server. It's an indispensable tool for bridging the gap between local development and cloud-based AI agents. Providing files to an agent through a process called Retrieval-Augmented Generation instantly creates a specialized expert on that specific topic. You can upload a dense technical manual, a legal document, or even an entire book, and the agent will use that content as its primary source of truth. This allows you to create hyper-focused agents that can answer questions with incredible accuracy and detail. Retrieval-Augmented Generation, or RAG, is a powerful technique that grounds an agent's responses in a specific set of documents, dramatically reducing the risk of factual inaccuracies or hallucinations. Instead of relying solely on its general knowledge, the agent first retrieves relevant passages from the provided files and then uses that information to construct its answer. This ensures the agent's responses are both accurate and contextually relevant. A knowledge-enabled agent can transform a static document, like a dense textbook, into a fully interactive learning experience. You can ask the agent to explain complex concepts in simple terms, generate practice problems, or even create plots and graphs to visualize the material. This turns passive reading into an active, engaging dialogue with the text itself. A team of collaborating agents almost always outperforms a single, monolithic agent because of the power of specialization and diverse perspectives. Just like a human team, you can assemble a crew of agents with different release: a researcher, a writer, a critic who can work together to tackle a complex problem more effectively. This multi-agent approach leads to more robust, creative, and well-vetted solutions. Microsoft's AutoGen pioneers a conversational multi-agent framework where agents interact with each other through natural language to solve complex tasks. This framework allows for dynamic and flexible collaboration, as agents can delegate tasks, provide feedback, and work together in a way that mimics human teamwork. It's a powerful paradigm for building sophisticated, autonomous agent systems. In AutoGen's proxy pattern, the user proxy agent acts as the orchestrator, taking a task from a human user and coordinating the work of one or more assistant agents. The user proxy is responsible for validating the results from the assistants, providing feedback, and ensuring the final output meets the user's requirements. This pattern creates a clear separation of concerns and a robust system for task execution. The feedback loop between the user proxy and an assistant in AutoGen is an iterative process of refinement. The assistant proposes a solution, often in the form of code, which the user proxy then executes and evaluates. If the solution is not satisfactory, the user proxy provides feedback to the assistant, which then revises its approach until the task is completed successfully. Crew AI offers a more structured, role-based system for multi-agent collaboration, which contrasts with AutoGen's more free-form conversational model. In Crew AI, you explicitly define agents with specific roles, goals, and backstories, creating a highly specialized team designed for a particular purpose. This enterprise-focused approach is ideal for building robust and predictable agentic workflows. The core components of a crew AI system are the agents, the tasks, and the process. Agents are defined by their roles and goals. Tasks describe the specific work to be done, and the process dictates how the tasks are executed, either sequentially or hierarchically. These three elements form the fundamental building blocks of any crew AI crew. The fundamental difference between sequential and hierarchical task processing in crew AI lies in the flow of control. In a sequential process, tasks are executed one after another in a predefined order. In a hierarchical process, a manager agent coordinates the work of other agents, allowing for more complex and dynamic task delegation. Both AutoGen and Crew AI provide powerful frameworks for tackling complex, collaborative tasks like software development, but they do so with different philosophies. AutoGen's conversational approach allows for more flexible and emergent collaboration, while Crew AI's structured, role-based system provides more control and predictability. The choice between them depends on the specific needs of the task and the desired level of autonomy. AutoGen's group chat feature allows multiple agents to collaborate in a shared conversational space, which is far more dynamic than simple proxy patterns. In a group chat, all agents can see the entire conversation history, allowing for more organic and context-aware collaboration. This is particularly useful for complex tasks that require a high degree of coordination and shared understanding. Including a dedicated critic agent in a software engineering workflow provides immense strategic value by introducing a crucial layer of quality control. The critic's sole purpose is to review the code generated by other agents, identify potential bugs, and suggest improvements. This automated code review process leads to higher quality, more robust, and more secure software. AutoGen's caching mechanism is a critical feature for efficiency, as it stores the results of previous computations and conversations. This dramatically reduces token consumption on subsequent runs of the same task and makes it feasible to undertake long-running, complex tasks that would otherwise be prohibitively expensive. It's a key feature for making agent systems practical and affordable. In Crew AI's assembly line approach, you create highly specialized agents by defining their roles, goals, and backstories with a high degree of specificity. This allows you to construct a crew where each agent is an expert in a particular part of the workflow, leading to a more efficient and effective overall process. It's a powerful way to build a team of virtual specialists. In Crew AI, a task is the fundamental unit of work, linking a specific agent to a detailed description of work and a clear expected output. This explicit linking ensures that each agent knows exactly what it needs to do and what the successful completion of its task looks like. It's a core concept for creating clear and accountable agentic workflows. In a hierarchical setup within Crew AI, a manager agent is responsible for coordinating the work of the entire crew. The manager breaks down a high-level goal into smaller tasks, delegates those tasks to the appropriate agents, and then synthesizes their work into a final result. This allows for the autonomous execution of highly complex, multi-step projects. Monitoring the internal state, performance, and especially the cost of a multi-agent system is absolutely critical for production use. Without proper observability, it's easy for costs to spiral out of control or for the system to get stuck in inefficient loops. You need to be able to see what's happening under the hood to ensure your agent system is running efficiently and cost-effectively. Platforms like AgentOps provide crucial observability into the inner workings of a multi-agent system, offering detailed insights into agent performance, token usage, and overall cost. By tracking every step of the agentic workflow, AgentOps allows you to identify bottlenecks, optimize performance, and manage the economics of your agent system. It's an essential tool for moving from prototype to production. A high repetition of thoughts in an agent system is a clear indicator of an underlying design flaw, often suggesting that the agent is stuck in a loop or lacks a clear path forward. This can be fixed by refining the agent's goals, providing more specific instructions, or even restructuring the overall workflow. Detecting and addressing this kind of inefficiency is key to building robust and effective agent systems. The universal mechanism that allows an LLM to execute functions in the real world is a structured action framework, where the model can declare its intent to call a specific tool or function. This framework acts as a bridge between the world of language and the world of APIs and code. It's the fundamental building block for creating agents that can take real-world action. The OpenAI function specification provides a standardized way for an LLM to translate a user's natural language request into a structured API call. The LLM analyzes the user's intent and then generates a JSON object containing the name of the function to call and the arguments to pass to it. This is the core mechanism that enables function execution. The two-step call for executing a function begins with the LLM responding with a structured request to call a specific function with certain arguments. Your application code then executes that function, retrieves the result, and sends it back to the LLM in a second API call. The LLM then uses this result to generate a final natural language response for the user, completing the request response cycle. Microsoft Semantic Kernel is a powerful open source SDK that provides a comprehensive framework for building and orchestrating AI plugins and functions. It acts as a sophisticated abstraction layer, allowing you to seamlessly integrate your own code, external APIs, and prompt-based functions into a cohesive AI application. It's a game changer for building complex, production-ready agent systems. The core responsibility of the kernel and semantic kernel is to act as the central orchestrator, managing all the different components of your AI application. It handles the registration of services like OpenAI, the loading of plugins, and the invocation of functions. The kernel is the brain of your semantic kernel application, tying everything together into a coherent whole. Building a robust and reusable library of agent capabilities with semantic kernel involves creating a well-structured collection of plugins, each containing a set of related functions. You can create plugins for interacting with specific APIs, performing data analysis, or even managing user profiles. This modular approach allows you to build a powerful and easily maintainable library of agent actions. The fundamental difference between a semantic function and a native function in semantic kernel is their underlying implementation. A semantic function is entirely prompt-based, defined by a natural language instruction that is sent to an LLM. A native function, on the other hand, is defined by actual code written in a language like Python or C#, allowing it to perform any action your programming language can. The true power of semantic kernel is revealed when you embed native functions directly within your semantic functions, creating incredibly powerful and dynamic prompts. You can, for example, Have a semantic function that calls a native function to get the current date and time, and then uses that information to generate a personalized greeting. This function synergy allows you to build prompts that are both intelligent and context-aware. You can use a set of native functions within semantic kernel to wrap an entire external API, effectively creating a fully conversational GPT interface. Each native function would correspond to a specific API endpoint, and the kernel would be responsible for routing the user's natural language request to the correct function. This is the ultimate expression of the power of semantic kernel, allowing you to make any API fully conversational.